I'm Jingyue from Google. Anyone dealing with the noise here? Don't know what's happening. Anyway, so I will present gpucc, which is an open source general purpose GPU compiler targeting CUDA. And it's a collaboration with a lot of my teammates at Google. And they're super awesome and at the same time just so nice. So I want to give you a first give you a one-slide overview of the entire talk. So we decided to build gpucc because we see the need of that from both academia and the industry. So for academia, because people don't have such an open source compiler, I see a lot of optimizations that should appear on the IR level have to be put into the source-to-source translation and even assembly translation, which are very complex and fragile, not unnecessarily. It's not the only problem for research, it's also a problem for industry because large data center operators want to avoid vendor-provided binaries as much as possible for many reasons. For example, we want to avoid reduce binary dependencies. We want to be able to tune the compiler towards the workloads we care about. We want to enjoy new language features, even if it's not supported by the vendor-provided compilers. And also, finally, we want to shorten the bug turnaround time. Once we find a bug in the compiler, we don't want to spend a long time communicating with the vendor on where the bug is, etc. To solve all these problems, we built gpucc, which we believe is the first fully functional, open source, high-performance CUDA compiler. It is built on LLVM, so it automatically supports language features like C++11 and part of C++14. In terms of optimization, we developed and tuned several general and CUDA-specific optimization passes. So as a highlight of the results, compared with nvcc, which is the closed-source compiler NVIDIA provides, the code generated by gpucc runs up to 50% faster on our internal end-to-end benchmarks. The performance is on par on a variety of open-source benchmarks as well. The compile time is also faster. We are 8% faster on average, and for some very long compilations, we're 2.4 times faster. So in the remaining of the talk, I'm going to talk about the architecture of gpucc, and then the optimizations, which are the focus of this talk, and finally some evaluation results on the performance, runtime performance, and compilation time. Before I dive into the architecture, I want to give you a taste of how CUDA looks like for those of you who are not familiar with CUDA. CUDA is a language and a platform created by NVIDIA for you to program GPUs. The language itself is quite similar to C++, except for some CUDA-specific syntax and intrinsics, etc. So a typical CUDA program will wrap the computation the user wants to offload to GPU in the CUDA kernel, right? Essentially a function that's annotated with this global attribute indicating it's going to be run on GPU. And then on the host side or CPU side, the program may allocate a piece of memory on the device and copy the data from the host to device and launch a kernel using this triple angle brackets syntax. And when the kernel finishes, it copies the results back from the device to host and keep processing other data and maybe launching even more kernels. So a very nice feature about CUDA is that you can mix the host and device code in one single translation unit, right? And it's a very desirable feature because now you can do fancy things like template instantiation across host and device. And that's very important if you want to propagate constants from host to device, because the kernel launch is not simply a function call. It's more complicated than that. It's a nice feature for the programmers, but on the other hand, a very difficult challenge for the compiler, because think about it, Clang has to parse the source code with different contexts in mind, right? Because CUDA and C++, although similar, are not exactly the same. So to address this challenge, the current and interim architecture of gpucc borrows the idea of separate compilation from nvcc. So given the mixed mode input file that has both host and device, we have a host key component called host device splitter. that splits the input file into host code and device code. And then on the device side, we run Clang, which already supports a lot of device-only CUDA code, generating LLVM-IR and run the optimizer, and finally run the nvpx codegen, which is a component NVIDIA open sourced, I think a couple of years ago, that translates LLVM-IR into ptex assembly in the stream format. And then we embed this ptex assembly in the stream format in the host code and compile it, again using Clang, but this time as a regular C++ compiler, and generates a binary. So this architecture has been working for quite a long time, but it has issues. The most important issue is the splitter uses source-to-source translation, so which can be complex, which is actually very complex and fragile. A lot of bugs go into that component. And the second reason is the compilation time is going to be long, because you need to parse the source code for 3 times, once by the splitter, and once by host compilation, and the third time by device compilation. So in the long term, we're going to integrate the entire compilation flow into Clang driver. Artem Belovich is the main person who's driving this effort, and after this is done, you can just compile CUDA mixed code using Clang, just as the way you compile a regular C++ code. It's going to be very easy and very elegant. The only drawback is we don't have a name anymore, because people will say Clang compiles CUDA instead of GPU-CC compiles CUDA. It's going to be fine. Next I'm going to talk about optimizations. When we started this effort, LLVM had been well-tuned for CPUs, but not for GPUs. There are very little work public on optimizing LLVM for GPU. So initially, we started by just running -03 on GPU code and see how it performed. It turns out the result is really bad. A lot of times, you will end up with code that runs over 10 times slower than nvcc. So we investigated what's going on there and figured out the root cause is actually the difference between these two architectures, right? So these CPU and GPU has completely different design philosophy. CPU is designed for general purpose and optimized for latency, and the GPU is designed for graph rendering and designed for throughput, because rendering is highly parallelizable. And as a result, CPU usually have very heavyweight hardware threads that has branch prediction, out-of-order execution, and superscalar, etc. But GPU has none of these. Because CPU threads are more heavyweight, it can deploy a lot of cores on a single chip, while GPU can deploy tens of thousands of cores on one single GPU chip, enable massive parallelism. And because the difference in hardware, the ISA is also different, and the performance of each single instruction is also different. All these map to why we need the compiler to make different decisions for GPU programs. So we investigated the performance gap between GPU-CC and nvcc originally, and we developed and tuned some existing optimizations and new optimizations. And here's a list of the major optimizations we do in GPU-CC. I'm going to focus on the first 2 and just briefly talk about the remaining 4. All these are open source, by the way. The first item is a straight line scalar optimization. So it's actually a set of 3 smaller optimizations that share the same theme of reducing redundancy in straight line code. So why is straight line code so important? This is because, again, the GPU architecture, because it doesn't have branch prediction, doesn't have out-of-order execution, the control flow transfer is really expensive. So this is why both the compiler and the programmer will encourage loop unrolling. And in LLVM's pipeline, loop unrolling appear at a very early stage. So after that happened, you must deal with straight line code. So in this talk, I'm going to use a running example to show you why it's important and how each individual optimization works. So this example is very simple. It basically loads a 3x3 submatrix from a larger matrix, n by n, right? And although it's simple, it's very common pattern in GPU programming. Think about a matrix multiply. Usually divide the input matrix in several portions, and each thread loads its working set, work on it, and writes the result back. So very common pattern. Let's also assume the loop body is very small so that the compiler chooses to unroll it. And in fact, sometimes programmers even put the unroll annotation there, saying the compiler must unroll it for performance reason. And after you unroll it, you will see not only one P, but 9 different versions of P computing the value in different loop iteration. And if you just handled it, if you just pass this code to LVM and nvptext before we work on the straight line optimizations, they will generate very bad code for that. And the reason is because the generated code simply naively follow the order in the source code. For example, to compute P8 here, it first computes C plus 2, and then B plus 2, and then times n, and then adds the result, and then finally adds the byte offset to the base address of A, right, taking at least 5 instructions. But if you look closely, there are clearly some missed opportunities. The first one is it doesn't leverage the adjacent mode, the base plus immediate adjacent mode that ptext ISO provides. So if you slightly rewrite the pointer arithmetic in a different way and extract the plus 2 out, you can actually fold this plus 2 into the adjacent mode instead of using extra instruction to compute it. And the second opportunity is what I call injured redundancy. It's borrowed from from a SSA PRE paper. And it says you have 2 instructions in this example, for example, B plus 2 times n and B plus 1 times n. They're not exactly the same, but very similar. Only the constant part is different. So you can essentially rewrite B plus 2 times n into B plus 1 times n plus n, so that you only need one extra instruction, right? Because B plus 1 times n is already computed in P3. So to leverage these missed opportunities, we developed 3 new optimizations. The first one is a pointer arithmetic reassociation that targets the adjacent mode issue. And the other 2 are straight line strength reduction and global reassociation targeting the injured redundancy issue. So next I'm going to apply these 3 optimizations on the running example to show you how they work. Pointer arithmetic reassociation, I already sort of suggested a little bit. It works by reassociating the pointer arithmetic expression into the sum of a variable part and the integer constant offset, so that the integer constant offset can be folded later into memory operations. And besides that, another benefit of pointer arithmetic reassociation is the variable part from different loop iterations can usually be reused, right? So like in this example, P0, P1, and P2 share exactly the same variable part, so you can just combine them. So after doing that, we do straight line strength reduction. So the idea is similar to loop strength reduction, but focusing on straight line code instead of loops. It works by matching and replacing some code patterns. One of the patterns, for example, we target is if you have 2 instructions, x and y, both are computing base plus constant times the stride, and base and stride are the same, only the constants are slightly different. And also x dominates y. There are a lot of conditions on that. Then we can rewrite y into x plus the difference of the difference of the constants times stride. And doing this is usually beneficial, is because in practice we see a lot of times C1 minus C0 is 1. And even if it's not 1, because it comes from loop unrolling, it is usually the same across different loop iterations, so the cost can be amortized, right? But there are drawbacks. I don't suggest you blindly apply this transformation, because originally you see x and y don't depend on each other, but after this optimization, y depends on x. So you introduce extra dependency, which may hurt pipeline, etc. But it's not a big problem for GPU because there's no pipeline there. So after applying this rule to the result of pointer arithmetic reassociation, we simplify x1 into x0 plus n and x2 into x1 plus n. The code becomes much simpler. The third optimization is global reassociation. And so LVM already has a reassociation path, what I call local reassociation. It works by processing each expression individually, right? And then reorders the operands according to some heuristics, or what they call ranks, which may or may not reflect the real how these operands are actually reassociated in other instructions. The difference of global reassociation is it considers how the operands are actually associated in other instructions, so that in a lot of cases it make better decisions. And in this example, let's focus on x0, I0, which is the index of P0, and also x1, I1, which is the index of P3. If you look closely, I1 is essentially computing C plus x0 plus n, right? And C plus x0 is already computed by by I0 before. So if you can reassociate I1 towards that, then you can simplify I1 just as I0 plus n. And by the way, this cannot be done by the local reassociation pass, because they will assign C and n a very low rank because they're function parameters, and choose to associate them first, and then miss this optimization opportunity. The same idea can be applied to pointer arithmetics as well, because down under the hood is just a bunch of adds and multiplies. So if you continuously apply the similar idea to P3, you can rewrite P3 into P0 plus n. So code becomes even simpler. So this is what the code ended up with, right? Compared to the original code, like what's on the left, it's way more simpler. So each P, I think except P0, all the other Ps can be computed using at most one extra instruction. It's much better. The example here I gave is very simple, but there are a lot of implementation challenges. For example, how do you deal with integer extensions, sign extensions, and how do you make these algorithms very efficient running in linear time, for example. And I wrote a design doc on all these optimizations, and you can take a look about all these details. So the next optimization I'm going to talk about is inferring memory spaces. So memory spaces are a special notion in CUDA. It used to refer to different hardware components, different logical components in hardware. The graph here shows you a simplified architecture of GPU. So you have a GPU device that has multiple blocks. Think of it as CPU processors if you're not familiar. And each block has multiple threads. Think of it as CPU cores. And all the threads, all the blocks share the same global memory. But at the same time, each block has its private shared memory that's shared across all the threads in the same block, right? And shared memory is much smaller, but also much faster to access than global memory. So in order to enable software control of these different memory components, the ptex instruction set provides several special load and store instructions. For example, you can do load shared, store shared, if you know the address you're accessing must be in the shared memory, right? And similarly, you can do load global and store global if you know it must be in global memory. And they will be much faster. So if the compiler doesn't know like which memory address space or which memory space the pointer is in, it can always do a generic load and stores, and it will at runtime check the memory space and doing the corresponding load and store. But it pays the runtime overhead of checking, and also the alias analysis will suffer because the generic space aliases all memory spaces, and the JIT compiler in the CUDA driver cannot like reorder instructions as freely as with special loads. So this is the performance difference is actually the main motivation of this optimization of inferring memory spaces. So this optimization works by, the idea is to go through the code and find out all the pointers and try to infer which memory space it resides in. So in this example, we only have one load, which is v equals star p. And if you like the pointer p, it's a pointer induction variable, but its underlying object is always a, right? And a is annotated by the shared attribute, which is a programmer added to indicate that a must be in the shared memory. So the compiler can just generate a load shared for V equals star P instead of a generic load. Although the idea is simple, implementation-wise, so dealing with pointer induction variable is not that easy because it's in LLVM-IR, it's a fine node, depends on some initial values and some incremental values, and finally depends on itself, right? So in order to handle that case, we created a fixed point data flow analysis that doing this iteratively. Again, this is described in a design doc. So I talked about straight line optimizations and memory space optimization. There are some other optimization I want to talk about. They're not as complicated, but also very, very important. The first one is we do more aggressive loop unrolling and function lining. And the reason is, again, is the control flow transfer in GPU is much more expensive. So we need to usually need to deploy higher threshold. And we also allow programmers to use pragma unroll and force inlining to instruct the compiler to force unrolling loop or inline function. By the way, pragma unroll was added by Mark Heffernan, one of my teammates. This pragma is not only for CUDA, you can use it for any language using Clang. It's integrated already. The next one is memory space alias analysis. It's done by Xue Tian, who used to be my intern. And the idea is treat different special memory spaces, for example, shared and global, don't alias. Then alias analysis can be improved. The next one is speculative execution done by Bjark. And the idea is hoist instructions from conditional basic blocks so that it can promote straight line scalar optimizations, because straight line scalar optimization only look at like code that dominates each other. If it's embedded in the conditional block, it can't do that. But for sure, we only hoist instructions when it is safe, and also we have a threshold on the total number of instructions we hoist. Down the road, we need to apply better cost model, etc. on that. The last one is bypassing 64-bit divides. This is done by Mark again. And the motivation there is the 64-bit divide is actually much slower than a 32-bit divide on NVIDIA GPUs. So 64-bit divide spends more than 70 machine instructions, and 32-bit divides only spend around 20 instructions. So the optimization here is we add a runtime check before each 64-bit divide, saying if this is the runtime value of the operands are within 32-bit, then we just do 32-bit instead of 64-bit. The checking overhead is very small, only like 1 or 2 instructions compared to the cost of 64-bit divides. Okay, so finally talk about some evaluation results. We picked 5 end-to-end internal benchmarks. IC1 and IC2 are image classification. NLP 1 and 2 are for natural language processing, and MNIST is a handwritten digit recognition, very well known. They're all machine learning workloads, by the way. And for open source benchmarks, we pick Rodinia, Shock, and Tensor. The first one are very popular. Tensor is a module in the Eigen library, which is a templated CUDA C++ library for linear algebra. Very heavily templated code, very, very special compared to the other 2 benchmarks. Machine setup, we use NVIDIA Tesla K40C, and our baseline is nvcc 7.0. It's the latest version at the time of the evaluation. And actually, we started with nvcc 5.5, but then from 5.5 to 6.5 to 7.0, we see the performance actually degrades with each upgrade of nvcc. So this, again, motivates our efforts of building an open source compiler. So first I'm going to show you the performance, runtime performance on the end-to-end benchmarks. The metric here I'm using is the runtime of nvcc version divided by the runtime of GCUDA-CC version n-1. Right? So the higher the bar is, the better GPU-CC performs. So the speed up of all the 5 benchmarks range from 10% to 50%. So we're faster on VCC on every one of them. And the geomean is around 23%. We run the same experiments on the open source benchmarks. So here I order these benchmarks according to the speed up, but I use different colors to represent the benchmarks from different suites. So red means Rodinia, green means Shock, and the blue means Tensor. So as you can see, the Tensor, well, you can't see it, but I tell you the geomean speed up of Tensor is 3.7%, and Rodinia is slightly faster. Shock is slightly slower. Okay, so the result here is not as great as what we have for end-to-end. I believe, because we just didn't spend enough time on it. It's basically my intern spent 1 month, and he achieved this result, which I'm very surprising actually. So this is, again, motivates the effort of open sourcing, because you guys, all the LLVM contributors, can contribute to this compiler and make it better on the benchmarks you care about. So finally, the compilation time. We are 8% faster on average than nvcc. This is a per translation unit average, by the way. And there's one interesting kernel. It's a very heavily templated kernel, so it expands to very long code. And nvcc spent like more than 250 seconds on it. Well, GPUCC only spent slightly more than 100 seconds on it. That translates to 2.4 times speed up. And we also did a breakdown of the compilation time and noticed that there are more than 30% of the time spent on device splitter and host splitter. And this means after we do the integration, this time can be reduced a lot. So we should be even faster after the Clang integration is done. As a conclusion, I presented GPUCC, a fully functional, open source, high-performance CUDA compiler. It enables reproducible GPU compiler research and architectural research, high-performance computing research in general. It also, industrial-wise, it makes the deployment of GPUs in restricted and controlled environments much easier. So I believe a lot of the concepts of insights from the optimizations are general and applicable to other GPU platforms. And in fact, some of the straight-line optimizations have already been adopted to PowerPC and ARM64-bit architecture. And I think AMD GPU is also experimenting with some of these, but they didn't really upstream. I saw some patches floating around, so I'm speculating. So as an open source effort, the future work is we want to get the Clang integration done. It's actually pretty close, but not there yet. We also want to have a target-specific optimization pipeline, because we did modify the orders and add several new optimizations in the pipeline. We also want to support CUDA driver-only runtime, because we want to avoid depending on the CUDA runtime API, which is another binary blob, but we want to avoid. Finally, lots of documentation and packaging so that people can use it. I think I still have some time, so because the Clang integration is not done yet, so right now, if you really want to try it immediately, you could, but you need to do the splitting yourself. You need to split the device and host code yourself. So here I have some examples. So this is the device code doing simple XP, and then you can run this clang-cc1 command. Just pay attention, you need to pass in the right include path into it. And then you run LLC to compile the LL into, the ptext file with the optimizations. And on the host side, you can write just a regular C++ code, but you need to hard code the name of the ptext file and the kernel name into the host code so that you can load it and launch it. And finally, you just compile it using Clang++ as a regular C++ program, linking the CUDA driver APIs, etc. This is how you would do if you want to try it right now. I will have a documentation page on this, and also once the Clang integration is done and can be used, I'll update the page and let you know in any means. All right, so with that, I'm open to your questions.
So really basic question, I guess. Does this mean that going through the new tool chain, you can compile CUDA programs to run on GPUs other than NVIDIA GPUs?
So I think we haven't explored that area like on other GPUs. But I mean, LLVM already supports AMD GPU. It's a backend there, so they could potentially like target the IR to AMD GPUs as well. We just didn't try that yet.
Just one comment. Have you tried your compiler on other NVIDIA devices? I mean, assume that NVIDIA tries to do optimization as general as possible to perform as good on as many devices.
Yeah.
And this could be one explanation that on that particular devices, your optimization are slightly better.
Yeah, I guess the question is whether our optimization are restricted to certain architecture, right? I mean, sub-architecture of NVIDIA GPU.
Historically, like companies try to do their optimization, especially if they have many hardware to care about, as general as possible, right? And you just present only one particular device. So I'm just curious, have you done experiments with other devices, other NVIDIA devices, just to be your case to be more convincing that you're improving actually above the NVIDIA compiler?
We tried K40 and K20, and they are about the same. So I don't think I comprehensively evaluate all the benchmarks, but we do pick some of them. And in terms of optimization, I don't think we sort of overfit to one architecture. I mean, just design purpose. We may end up happen to do that, but this is not our intention. Yeah. And also, NVIDIA, so I talked about PTEX assembly, right? But it's not really low level, very low level. It still has virtual registers. And NVIDIA has a PTEX AS tool that does like register allocation, instruction scheduling, and compile PTEX into the real machine code. So there will be a lot of hardware-tuned optimization on that level, but not really necessarily in the LVM-IR to PTEX translation.
I check this one. So a related question now, when you show a list of optimizations, for loop learning, you actually mentioned that it's using Pragma. So for different benchmarks, the programmers could set the different Pragma. So how much that impact your overall performance?
I think not very much. So the question is how many Pragma on roll we added to these benchmarks. I didn't count them. Very few for the open source benchmarks. And for internal, we added some, but it's not only for GPU-CC, but also for nvcc as well. And sometimes we even if the compiler can unroll some loops in the proper way, we still add that because we know like unrolling this loop is very important for performance. And even if later you increase the loop body, for example, we still want you to unroll it.
Yeah, and also loop and learning actually it's closely tied to the architecture. So if you're over enrolling, and you might increase the register pressure, which
yes, that's a trade-off we observed, but didn't have a very good way to solve yet.
Hi. Could you comment on the size of the C++ dialect that you accept versus what nvcc accepts?
Sorry, I didn't hear the size of what?
The dialect of C++ that you compile to the device. C++ features that you accept that nvcc does not, or vice versa.
Yeah, we see. So again, we only tried versions before nvcc 7.5. I don't know what they do there. But we also tried nvcc with, there's a flag saying enable C++ 11, but in fact, still a lot of C++ 11 features not supported correctly. So I believe functionality-wise, we're better than at least nvcc 7.0. Does that answer your question?
Well, I wanted to know if there were some cool features that you support that nvcc doesn't.
Examples of that, constant expression. Yeah. Let me think if there's something else. I guess you can continue questions while I'm thinking. I'll talk to you offline about it. Yeah.
Hi, so I'm using the nvptx backend from a different front-end language.
Yes.
And I'm wondering if I'll get the full benefit of these new optimizations or if there's anything special I need to do.
Okay, so the front end is different, but it's still like has a similar architecture.
I'm just generating LLVM bitcode directly and passing it to the nvptx backend.
Okay, I mean, the architecture-wise, are you using NVIDIA GPUs?
Yeah.
Okay, then I think it makes sense because all of our optimizations are on the IR level. So we're not doing like PTEX optimization, machine code optimization.
And they don't require any special annotations that you're making?
No, the only annotation is pragma on row, forcing line,
Great.
which runs on source code.
Thanks.
So just wondered if you could talk a little bit more about your plans for the runtime library when you finished working on the Clang integration. Do you think that will be like a new LLVM sub-project? Where do you sort of see that going?
I don't know what's the exact plan of how to upstream that, but I think the compiler itself can target that runtime and also the CUDA runtime. So it's just like something we wanted like internally or for data center operators. Yeah.
I guess my question is more about when you talk about a runtime, are you talking about designing a sort of a framework that you could plug in runtimes for like other devices if you wanted to?
No, this runtime is basically a replacement for the CUDA runtime API. Yeah, it doesn't do anything fancier than that. Chandra has some comments on that.
So I'm trying to speak on behalf of Artem. He couldn't be here, but my understanding is that it is a replacement for the CUDA runtime. We haven't really started the process of having a good discussion with where the upstream community wants it. I don't think there are any particular opinions about where it ends up. And it is a very generic kind of GPU-like runtime library, and so I think it would be easy to port to other targets. It does require some compiler support though, right? And so we'd have some switch on the compiler that says you're targeting this runtime library or this other runtime library. Does that answer your question? And certainly all of this will be discussed long before anything lands in tree. It's just we wanted to actually get Clang to support the existing CUDA tools first.
Thank you for this amazing contribution. Do you plan to go native to skip the PTX backend and generate native instructions such as Nirvana systems are doing and things like that?
Sorry, I didn't quite hear the question.
Oh, my question is, do you plan to add support to native NVIDIA instructions in the backend? To skip the PTX phase and optimize even further?
It's all nice extension to this project, but the answer is we haven't explored that area yet. So, yeah.
I think our time is up. Okay. Let's give the speaker a round of applause.